At the end of last lecture, we derived the compactness theorem, which turned out to be a pretty easy consequence of the completeness theorem. So the theorem says that if every finite subtheory T0 of a theory T has a model, then T has a model. So the proof is, again, very straightforward, because by the completeness theorem, we know that a theory has a model if and only if it's consistent. So if it turns out that T does not have a model, then it has to be inconsistent, but if it's inconsistent, it's already inconsistent for a finite subtheory. So this seems like a pretty simple conclusion from the completeness theorem, but it is a remarkably powerful theorem. And in this lecture, we're going to look at a few applications throughout mathematics, even beyond logic, that shows how powerful this theorem actually is. We start with one of the most famous applications, and that is the existence of non-standard models. So non-standard models here means non-standard models of arithmetic, but it also applies to other structures. For example, one could use a similar technique to obtain non-standard models for the reals, and those are then become the object of non-standard analysis. But to focus here on the non-standard models of the natural numbers, we look at the language of arithmetic, which has two constant symbols for 0 and 1, addition, multiplication, and less than. The theory of n, remember, is the set of all sentences that hold in the natural numbers, which we now call the standard model. And in order to construct our non-standard model, we make our lives a little bit easier by introducing this notation here. This symbol n underlined simply denotes the constant term 1 plus 1 plus 1 and so on n times. So this just gives us for every natural number a representation of that natural number as a constant term in our language. So what we do then is we extend our language. So we take our original language of arithmetic and add a constant symbol. This constant symbol C is different from all the symbols that are already in the language. And we call that language L prime. The idea now is to take the theory of n. So everything that is true about the natural numbers that we can express in the language of arithmetic. So there's a bunch of formulas in there and sentences. But now we add something new to this theory. Namely, for every natural number, we add the formula that our new constant symbol C is greater than the constant term n. Okay, so this somehow expresses that C is very big. In particular, it's bigger than any element expressed by the constant terms n for every natural number n. So what you should do now is verify the following. If you take a finite subset of this new theory T prime, argue that this finite subtheory T0 has a model. The key here is that the finite subset, right, will only have finitely many formulas of this form in it. Right? And some formulas from this part, but for this part we know we already have a model. The key is now that if we only include finitely many here, we can find a model for this T0 by interpreting C as a sufficiently large natural number. So I recommend you go over that for a moment, take your time, and make sure this all checks out. Now, since every finite subtheory T0 of T prime has a model, by the compactness theorem, we then infer that T prime has a model. Let's call that model M. But this model M needs to interpret our new constant symbol C. Let's call this interpretation in M, let's call it A. By the definition of T prime, so remember T prime includes all of these sentences here, it has to hold that this interpretation of the new constant symbol has to be greater than the interpretation of all those constant terms n, for all n. So what we've done is we've added a really kind of big element here. So A is an element that is greater than the value of all the constant terms. And then if we drop our new constant symbol C from the language and restrict our model M to the original language of arithmetic, what we get is a non-standard model of arithmetic. It satisfies the exact same sentences as the natural numbers, but it is not isomorphic to n. And the reason for this being is that we have this element A. I mean, that still remains in the model, even though in the restricted language we don't have a name for it, but it's still there in the universe. That element cannot be mapped bijectively to anything in n, while preserving all the properties that n satisfies. For example, in n it's true that 1 is less than 1 plus 1, or that 1 plus 1 is less than 1 plus 1 plus 1. So all of these properties have to be true for the interpretation of those constant terms in our model M too. Furthermore, for example, n satisfies that there is no natural number between 1 and 1 plus 1. And we can express this property as a first order formula. Similar, there's no natural number between 2 and 3. So this also has to hold for our non-standard model M. So if you extend these arguments a little bit, you will see that the structure of M actually looks like having an initial segment that looks exactly like the natural numbers, but then there are arguments or elements that are like our A, that is bigger than all the natural numbers in M. And that's our non-standard element. So now if we were to find an isomorphism between M and N, A would have to be mapped into the natural numbers, but it would then have to land between two natural numbers. And but by our construction, A has to be bigger than every natural number. So such an isomorphism cannot exist. So you can start thinking about now what this model M must look like, right? So if we have this A here, but every number can be added to itself, so there also has to be an A plus A, and that also has to be in the non-standard part. Also, if a number is not zero in the natural numbers, then it's the successor in terms of plus 1 of another natural number. So there has to be a number here that we could call A minus 1, and so on. So think a little bit about what the very fact that M satisfies the same sentences as N, but is not isomorphic to N, how does that affect the structure of our non-standard model here? And you'll see soon there's a very interesting picture that emerges from that. Another application of the compactness theorem has to do with axiomatizability, or rather non-axiomatizability. So we demonstrate this with the example of a torsion group. So a torsion group is a group in which every element has finite order. So that means for some n, this expression will be true for every element. So the question is, can we actually write down an axiom system for the torsion groups? Well, it's maybe a little bit surprising, as a consequence of the compactness theorem, we can show that the theory of torsion groups is not elementary. Not elementary means there does not exist a theory over the language of groups such that M is a model of T if and only if T is a torsion group. So the models of that theory would be precisely the torsion groups. The idea to prove this is as follows. Suppose we have a theory such that every torsion group is a model of T. So the theory in particular holds for every torsion group. It might hold for more. We then use a compactness argument to show that there exists a model of T that has an element of infinite order. So in particular, T cannot characterize precisely the torsion groups. So in particular, it cannot be an axiomatization of the theory of torsion groups. And the idea to prove this is quite similar to the construction of a non-standard model of arithmetic. So first, we start with our language of group theory and extend it again by throwing in a new constant symbol we call C. And then we extend our theory T that we started out with by saying, okay, if I multiply C n times by itself, I get something that is not the identity. So in this sense, this would be a witness that this element does not have order n. But I throw in this sentence for all numbers 1, 2, 3, and so on. So this would be kind of the analog of what we did before by throwing in the sentences that the constant C is bigger than the constant term n. And again, similar to how we argued before, it's not hard to see that any finite subtheory T0 of our new theory T star has a model. And so you should convince yourself that this is true. But then, once we have this, using the compactness theorem, we get that actually our big theory T star also has a model. So if we call this model M, then C has to be interpreted in M. So Cm has to be an element of our model. And by our construction, this C cannot have finite order because this is what we're excluding here. So I should probably add that we assume also that T extends the group axioms. So we make sure that every model of T star in particular is a group. So to sum up, we then get a model of our theory T star that is a group, but by construction contains an element of infinite order, namely the interpretation of this constant symbol C in our model M. The final application we want to give here is concerns colorability of graphs. So let's say we have a graph, which is just a pair of a vertex set and an incidence relation. So let's assume we have simple graphs. So this is a symmetric relation. And we say this is k-colorable if there exists a mapping from the vertices into this set, which you can think of as the colors, such that no two adjacent vertices have the same color. Okay, and the theorem we want to prove here as an application of the compactness theorem is that a graph G is k-colorable if and only if all its finite subgraphs are k-colorable. So of course one direction is immediate, right? If we know that the big graph is k-colorable, all its finite subgraphs are k-colorable too. But for the other direction, we use the compactness theorem. And it's all about, again, how to set up the problem so that we can apply the compactness theorem. So here we completely create our language from scratch, so to say. We start with adding a new constant symbol for every vertex in the graph. So the language will just have constant symbols, and the constant symbols represent the vertices in the graph. So that allows me to say something or express something about the vertices in the theory that I'm going to devise. So the theory that we're looking at now is just simply saying for every pair of vertices that are adjacent, I require that the value, right, of CV is not equal to the value of CW. So the model of this will simply be a set, right? In this set, the interpretation of the constants has to be different for adjacent vertices. Okay, so this will be simply then a map from the constants, right, to some set. But I also require, by adding this formula here, this formula simply says, okay, the set over which I interpret has at most k many elements, okay, because we want to have a k coloring. So if you haven't seen these number formulas, you should think a little bit about it. How could you express that a structure has at most k many elements? It's not hard to do in a first order formula. Okay, so we throw all of these into one big theory T, and then it's not hard to see that any model of T actually describes a k coloring of G, right? Because the coloring condition is reflected exactly in those formulas we add here, and that it's a k coloring is reflected in the fact that the model has at most k many elements. So now it's not hard to verify then that any finite subgraph of k being k colorable implies that every finite T0 subtheory T0 of T has a model. Right? Because the way we set it up, this translates into this. Okay. But now we have this, then applying the compactness theorem gives us that T has a model. And that translates in turn into a k coloring of our original graph. So you see here, this is an application of the compactness theorem that from the outset doesn't seem to have much to do with logic, right? But translating it into the right context in logic allows us to apply the compactness theorem and then immediately get the result that we wanted to prove from the statement of the compactness theorem.